Hello again. Before we start, somebody asked me if you are able to submit a PDF for the exam and then resubmit if you want to make changes. And my answer to that was that's highly not recommended because I might get confused about which file to use at the end. And it's best if you just make sure that whatever you submit to me by email is your final set of solutions that you're happy about. Also, I suggest using the time, unless you're in a hurry to submit. Just keep it in case your opinion changes. But of course, if you're really confident, you can always submit early. So today we'll start. Today we'll start talking about parameter estimation. So yesterday we finished off by mentioning this maximum entropy principle that aims to find a PDF for a random vector that satisfies certain equality constraints about expected values of various functions of that PDF, of that random vector. And that turned out to be an exponential PDF, where the exponent has those statistics that were used in the constraints as basis functions. So in general, people don't use that method. I think it's actually a pretty good method for density estimation, but it's not very popular in machine learning. I just mentioned it so you know about it. Typically, people use variations of Bayesian parameter estimation techniques. The most commonly used ones are maximum likelihood parameter estimation. I'm going to call it maximum likelihood estimates. So we'll call this the ML estimate and maximum a priori. So similar to the classifiers we talked about. So this will be map estimates. In fact, if you think of so remember, in the case of classification, we used these class conditional generative PDF models for data X, given the class label is L, in combination with the prior probability of label L being picked to generate data, right? So, and our overall data model is like this, right? So my data vector X is generated from this mixture of class conditional PDFs, where the class priors are mixture linear combination weights. And for each class label L, I pick with some probability that label, and then I generate a random vector X from the distribution of that particular class, right? So you can think of these class labels actually as parameters, right? In fact, if these were Gaussian distributed class labels, right? So here you would put, for example, a Gaussian PDF like 2 pi, let's say X is n-dimensional. So negative n over 2. So this function here could be something like covariance for class L, e to the power, right? So there's a mean vector for class L. Right. So in the classification problem, we assume that we know these for each class label. We know these particular mean and covariance parameters, the values, and what we don't know when an X vector arrives is which of these L values, which of these mu L sigma L pairs generated that data, and that's what we're trying to estimate. So classification is really a special case of parameter estimation, right? Where we're estimating a parameter that takes, in this case, integer values, right? So from 1 to capital L, for example. So we're going to generalize from estimating class labels, which are one special case of parameters, to actually estimating these real valued parameter sets. Right? So either vectors or matrices, or maybe even tensors. So we will use exactly the same approach. We'll start with expected loss minimization. So we'll call it Bayesian parameter estimation, like we did for classifiers, parameter estimation. And suppose I have a data vector x, which is drawn from a PDF with, I'm going to use this notation, with parameter vector theta. Right? So in the case of a Gaussian, as we have seen before, the unique parameters that characterize in this expression are the entries of the mean vector and the unique entries of the covariance matrix, the diagonal entries and one of the triangles, upper or lower triangular portions. Right? So those are the unique parameters that need to be estimated in order to define this Gaussian PDF function. So if I stack all of those parameters into a vector and call it theta, so the problem of parameter estimation is, given some data samples that are drawn from this distribution, estimate what those parameter values are that could have generated those values. Right? So let's, in the practice exam, practice questions, I think I suggested that, if I remember correctly, suppose you have these vector samples. Let's say these are drawn in an independent, identically distributed fashion from a Gaussian with mu parameters mu and sigma. And let's say this mean vector is unknown, and this is known. So I know the covariance. I know that these data samples came from a Gaussian. I know what the covariance is. I don't know what the mean is, and I would like to estimate. Right? So in the practice exam, I suggested that you can estimate mu by taking a sample average, right? So for over these vectors. So this could be n-dimensional. This could be, I don't know, m-dimensional. So everything can be vectors here. But in this case, so the mean vector will be an n-dimensional vector, and the suggestion was to just take this sample average, right? So, and you probably did this in some contexts. So the question is, why were you doing it? Right? Is that a good estimator of mu? And if you claim it's a good estimator, my next question will be, in what sense it's a good estimator, right? So you cannot just say it's a good estimator. You have to say, according to this objective function, this is the optimal estimator, or it gets close to the optimal estimator with this much potential error, right? So you need to be more specific about those claims. So in Bayesian parameter estimation, we'll try to minimize expected loss. So this is essentially a function of the data, right? So it's you can think of this parameter estimator as so you can see here that it's a function of your data set. So in general, we will here have some data that, according to some optimization, by solving an optimization problem, hopefully, it will give us an estimate, which will be a function of the data, right? Since the data samples are random, and this is a function of those random quantities, the estimate itself is a random quantity, right? So that's why in the exam, in the practice questions, we can talk about the expected value of mu hat. It's random, so it has an expected value, and it has a covariance, right? So you can talk about statistics of this random quantity. So in Bayesian optimization, we'll try to do the following. So I'll try to come up with an estimator which minimizes among all possible values, or all values that are legitimate, acceptable, right, or feasible, So I'm going to say all values that are feasible. So minimize some kind of cost. Let's call it loss associated with estimating theta hat from data when the true parameter is theta true. Okay. So the data was actually generated by a PDF with this theta true parameter. I did my estimation calculation here, and I ended up with this particular estimator, which is some function of the data. And there's probably a mismatch here. I mean, this is a fixed quantity. This is something that's random. It will depend on the data. Right? So there's going to be some mismatch here, and I can compute some loss. Right? So loss could be, for example, if these are vectors, maybe you're interested in, theta true minus theta hat. Right, so maybe you're interested in minimum mean squared error parameter estimation, and that's the loss function here is this. Right, so this is the loss between theta true and theta hat. Right, it's squared error. So for different choices of this loss function, obviously the objective changes. So this optimization problem will give you different optimal estimators. Right? So there are 3 specific cases that are worth mentioning. Right? So if loss between the true and estimated parameter is defined right. So I'm going to mention 3 cases. So if the loss is this squared error, so if the loss is theta true minus theta hat L2 norm squared, then the optimal theta hat will become the condition. I'm trying to remember to make sure that I'm remembering correctly. So the estimator will be the expected value of theta given the data set. So it's going to be the conditional expectation. Okay. So if you're trying to estimate parameters to minimize expected squared error, what you should do is get the posterior PDF for the parameters conditioned on the data that you have observed, and the expected value of theta in this conditional will be your optimal estimator according to this loss function. So I'm going to write this as mean of this conditional PDF. Right? So it's the mean value. If you choose loss to be the L1 norm of the error, so if you choose the loss to be theta true minus theta hat L1 norm, right? So you want to minimize expected L1 error, L1 norm of the error. Then the optimal estimator turns out to be, so let's call this theta hat 2, theta hat 1. So the optimal estimator turns out to be the median of the conditional distribution. So it's going to be median of theta given. So it's the posterior. You get the posterior of theta given data. Find the median of that conditional PDF. That's your estimator, which minimizes this. And if you choose your loss to be the L infinity norm of the error, so if you choose theta true minus theta hat L infinity norm, then I'm trying to remember if this should have a square or Yeah. I'm not sure if you need to have a square here or not. I think you need to. Okay, so the optimal solution ends up being the mode of theta given. So it's the mode of the conditional. So median of the posterior for the parameter given the data set is the optimizer for L1 expected error. So mean of the posterior is going to minimize L2 loss, and mode will minimize L infinity loss. So does everybody know the difference between median, mean, and mode for PDF? Anybody who does not know? Okay, so everybody's. Okay, so this last one here, yeah, not that one. So there is another loss that we'll use. Sorry, it's similar to the case before, 0-1 loss. I think I made a mistake. I'm trying to write from memory on the spot. I think I need to fix this. It's not going to be L infinity. It's going to be, yeah, and this will be a square. And this is, let me see. I'm going to just draw it. This is actually 0-1 loss. So true minus theta hat. So if this might be infinity wrong. Okay, so basically this, let's call this delta, negative delta. So if your estimate is very close to the true value, you incur 0 loss. If your estimate is slightly away from the true value, regardless of how far away, you incur the same unit loss, right? So you either get the correct value or not. If you get the correct value, you incur 0 loss. If not, you incur 1 loss, just like in the previous case. So this ends up being MAP, actually, maximum a posteriori parameter estimation, right? So okay, and let's talk about now this parameter posterior. How do you get that if you have data? So the problem will be typically given some data set. Let's assume these are independent samples, and they all come from the PDF P with parameter theta. Right? So, for example, this could be a Gaussian with some mean and covariance that need to be estimated. So how do I obtain P of theta given my data set, right? So that's my posterior likelihood of a parameter value theta after I have observed all these values. So we'll use Bayes' rule, right, to switch the ordering of these conditionals. So use Bayes' rule to get, I'm going to drop these curly brackets. Okay. So you can use Bayes' rule to express the parameter posterior in terms of data likelihood for a candidate parameter value times the likelihood of that candidate parameter itself from the prior, and divided by some normalization term, so that this ratio ends up being a PDF, and when you integrate over theta, it should integrate to 1, right? So that denominator is the normalization term. Since I'm assuming that my samples are independent and identically distributed, right, and they all come from this PDF, for the joint conditional likelihood here, I can use independence to write this out as product of marginal likelihoods, right, like this. And the prior is here still, and the normalization term is whatever it is. So, okay. So using independence of my data, I broke the joint into product of marginals. And if I have a prior, I'm going to use that here for p theta. And let's say we're doing map parameter estimation. So I'm interested in finding the parameter value which is most likely given the data set. Right, so map, let me just write on this side. Okay, so I'm going to do map parameter estimation, which is the mode of the posterior. So it's going to be the value of theta, which maximizes this posterior probability distribution. And from that expression here, if my data set is IID, right, this becomes maximize P. So I'm just going to make this a product. And PXI theta, and I have a prior, then like this, right? Just to clarify one thing, I was bothered here. The independence assumption here is a conditional independence assumption, actually. It's more appropriate to say x1, xi, and xj are independent for all ij pairs that are not equal, let's say. xd, so samples are independent from each other, conditioned on theta. Because we're treating theta as a random variable here, if I'm going to talk about independence in this sense, like it's the conditional PDF breaks down into its factors. So it's a conditional independence that I'm assuming here. Which is why I could not break this down as a product of marginals of xi's without the condition, right? So that's not the independence I'm assuming here. It's this. I'm assuming this independence. Okay. So my data is conditionally independent given the data parameter, which is not the same as xi and xj are independent regardless of the value of theta, right? So that's not the same statement. Okay, so back to here, because I'm going to be choosing the value of theta, which makes this quantity maximum. And since this numerator term here does not change with theta, right? It's the same. So this numerator here, just in case it's not easy to see what it is, this is basically your data set and the parameter in a joint. Right, so take the joint of your data and the parameter and integrate out the parameters. Let's say whatever the domain of that function is for theta. Right, so again, using Bayes' rule, you could think of this as the data likelihood, right? Condition on the parameter times p theta. Right, so this denominator is basically the numerator integrated over the values of theta. So it does not depend on theta anymore because of this marginalization process. So because it doesn't depend on theta, yes? It's overall the values that theta takes. I'm assuming they will be, if you're allowed to use all the real values, then negative infinity to infinity. If not, then whatever the allowed values are. So because this denominator does not depend on theta, it's the same constant value that divides the numerator for every value of theta. So I can actually ignore that. I can simply choose the value of theta that maximizes the numerator. Right, so in this particular case, my map estimate, right? So when I have n IID samples where the samples are independent from each other, conditioned, given the parameter, right? So that's the independence we're assuming. I can simply solve this optimization problem and get my map estimate, which minimizes expected 0-1 loss, right? Okay. So again, if somebody comes and tells you you should use map parameter estimate because it's awesome, it's optimal, no, it's not the best ever, always, right? So it's only going to optimize that particular expected loss function. So if that loss function is not what you care about, for example, if slight deviations are less costly for you, right? Slight deviation of theta hat from the truth are less costly for you than large deviations, like in the L1, L2 cases, you can actually have a monotonically increasing function as you get away from 0. So you penalize small errors less than large errors. So this estimator does not care how much the error is. If it's an error, you get penalized equally. So it's not necessarily the best ever for all situations. Okay, so, but people use it a lot. It's a good estimator in general. Yeah. How do you get the denominator? So let's just write it out maybe here. Okay, so can I just call this x so that I don't have to. So if you have here p of x in the denominator, you can always, since theta is another random variable and we assume there's some kind of relationship between x and theta, I can always do the following, right? So get the joint PDF of x and theta, and then integrate out theta. Let's say theta can take all the real values, if it's a scalar, or all the values in a real vector space. So you would just integrate over all possible values of theta, the joint PDF. And that would give you the marginal of x. But now, so you can always do this, right? So whenever you have a marginal, you can always introduce a second random variable, make a joint, integrate out that extra one. You're back to the first marginal, right? And from Bayes' rule, so let's say these limits are negative infinity to infinity. So from Bayes' rule, this would be x given theta, p of theta d theta, which is what we have in the numerator. Right? This is p of x given theta times p theta. So basically, the denominator is the integral of the numerator with respect to theta. So you take the expression in the numerator here, integrate with respect to theta. That gives you this, and that's the normalization constant. So this this division here makes sure that when you integrate this with respect to theta, you actually get 1. Right? Because this has to be a legitimate PDF, so it has to integrate to 1. And that division makes that happen. And that's actually just from Bayes' rule. If you see, if you move that over to the left side, what we have is p of theta given x, right, times p of x, which is the joint of theta and x, right, which is that. And so this times that is equal to the numerator there, p of x given theta, p of theta, and they are both equal to the joint. Right? So we started from Bayes' rule. I want the posterior, so the posterior is equal to these two divided by that. And and if you end up having multiple independent samples, that data likelihood breaks down into a product of individual likelihoods. So let's do an example. Maybe derive the sample estimator for the mean of a Gaussian, so that this all becomes more crisp. There is one more thing before that, though. So if you choose remember in classification, 0-1 loss minimization, expected 0-1 loss minimization led to the map classifier. So it's exactly the same thing here. Expected 0-1 loss minimization leads to map parameter estimation. On top of 0-1 loss, if you choose a uniform prior, right? Remember in classification, if the class priors were equal, right? That's a uniform prior. So if you choose a uniform prior, this is a constant. Right? So P of theta is a constant, so it doesn't depend on theta, and you can drop that, right? So this leads to the maximum likelihood parameter estimator, where you're just maximizing the likelihood of your data. So I'm going to just write it like this. So I'm going to maximize how likely x is for a given value of theta. Okay. So let's first derive the sample average for a Gaussian distributed random vector as an estimator for the mean using maximum likelihood estimation, and then we'll add a prior to the mean vector. And with that prior, that's not uniform, and then that will allow us to do map parameter estimation. Okay. So if I write cleanly, so we'll focus on map and ML parameter estimation a lot. So let me just write them out here. So my map parameter estimator is going to maximize the posterior of the parameters given data set X. Okay? And this is equivalent to solving the following, which is what we just talked about. So you can simply choose maximum likelihood times prior. Right? So the parameter value that maximizes this product. And maximum likelihood estimator is when you maximize only the likelihood part, because it corresponds to the case where the prior is uniform. Okay? So that's maximum likelihood. So because we have a product here, a product of a bunch of things, it would be nice to take the log and turn that into a summation. So expressions might be a little easier to deal with. So in this case, typically we will take the log of the objective. So this is equivalent to maximizing. So if I take the log of the objective, the best theta doesn't change, because whatever maximizes this value will also maximize log of this value. Log is monotonic, increasing. So if I take the log of the product, it's going to become log likelihood of the data under a parameter assumption here, right, plus log prior. So that's going to be my map estimator, typically, solving this problem. I'll get the map estimator, and we can do the same thing here, right? So I can take the log, I'll get the same optimal estimator, so I can maximize log likelihood. Okay. So typically we will do these versions with the logarithm. And when you have multiple independent samples, independence conditioned on the parameter being given, right? Then basically this likelihood term here, P of x given theta, will become a product of likelihood for each individual sample. When you take the log, it's going to become some log likelihood for each sample, right? So we'll see that for the Gaussian case. Okay, so let's say we have these samples that are IID from some Gaussian with mean mu, covariance sigma. The covariance is known, the mean is unknown, and this independence here means xi and xj. Two samples are independent, conditioned on mu, right? So if I knew mu, I already know sigma, I could generate those independent samples I and j. Okay, so let's write out this maximization problem. So the PDF of, so I'm going to maximize the log of PDF of all of my data conditioned on mu. Right, so that's my maximum likelihood estimator. Because these are independent given mu, this breaks down into a product of sorry, this is mu. This becomes the product of individual likelihoods for each data sample, right? And log of a product is a sum of logs, so this becomes maximize summation log pxi given mu. Okay, so each of those pxi given mu expressions are the Gaussian PDF with mean mu and covariance sigma. Right, so let's plug that in. So we're going to maximize with respect to mu summation. Okay, so I'm going to put here 2 pi. Let's say these are n-dimensional, small n-dimensional, so negative n over 2. Sigma is known, so I'll just plug it in here as a known quantity here. All right, so that's the normalization term, E negative 1 over 2, xi minus mu, minus mu. Okay, so that's the, and I'm missing a log, right? Squeeze it in here. So summation. So it's going to be ln of the entire PDF. Right? So let's break this product down into its 3 components, right? So I'm going to maximize with respect to mu. There's a summation. Okay. So log of 2 pi to some power. Right. So that's the first term, and then log of determinant of sigma to power negative 1 over 2, so that becomes minus 1 over 2 log determinant sigma. And the second term, log and exponential cancel each other out, so we're left with the exponent. So minus 1 over 2, minus 1 over 2 xi sigma inverse xi minus mu, right? So that's my optimization problem now. So let's keep that. Okay, so let's keep simplifying. So I have these are constants with respect to index I, right? So these 2 terms. So it's going to be capital N times the first term plus capital N times the second term. But they're also constants with respect to mu, right? So they're just additive constants to the sum of these third terms that depend on I and mu. So since these are additive constants and they don't change with mu, I can simply maximize the sum of those third terms equivalently, right? So equivalently, my maximum likelihood estimator in this case is, let me actually make this mu used to putting data. So this is my estimate for mu. So I'm going to maximize with respect to mu. I'm going to drop those additive constants. So we have from 1 over 1 to n. And that negative 1 over 2 can be taken outside the summation as a multiplicative factor. And we have this xi minus mu transpose xi minus mu. Okay. Right, so I need to solve this maximization problem. So this thing is a negative number times a positive number, probably. So I'm going to multiply with -2. So that's going to flip the objective. Instead of maximizing, I'm going to minimize -2 times this, right? So I'm going to minimize -2 times that. It will be summation xi minus mu sigma inverse xi minus mu, right? So this is now starting to look like sum of squared errors, right? So it's like a least squares problem. Okay. Each term in the summation is a quadratic polynomial of mu. Right, so these are quadratic polynomials. I add them up, so I still get a quadratic polynomial. Right, so I'm minimizing a quadratic function of mu with no constraints on mu. It can take any value in Rn. So I can take the gradient of the objective with respect to mu, equate to 0, solve for the location, right, where the gradient becomes 0, and that's my estimate. So if I take the gradient of the objective with respect to mu, I'm going to make it mu transpose, so it becomes a column vector. Remember, I like my gradients in rows. So gradient of the objective transposed okay, so that's the gradient of the objective equated to 0, right? So at the solution, this gradient will be 0. So let's take the gradient. So it's going to be, remember, if I have go to the matrix cookbook, I have a linear function of mu in a vector, multiplying a symmetric matrix in the middle from left and right to give me a scalar. So the derivative of this expression is 2 sigma inverse the linear part times the gradient of the linear expression here with respect to mu, which is negative identity, right? So I'll have -2 sigma inverse, and then the identity can be dropped since I'll have matrix times identity, which is matrix, whatever, right? So basically, oops. Sorry, let me just keep the summation. So I'm going to have here -2 sigma inverse xi minus mu. Yeah, I think that should be the gradient. And then at mu hat ml, right? So I'm going to plug in the value of the estimator. So I need to solve this. I have a -2 that can come out, and then we drop because I'm going to equate this to 0. So we have summation over index I, sigma inverse. Sigma here is a matrix, not to be confused with the summation sigma, right? Xi minus mu hat maximum likelihood, right, is equal to 0. Oh, yeah, sorry. Yeah. So this is a constant matrix. Again, doesn't depend on I, so I can take it outside. And because it's invertible, I can multiply with sigma, right? And basically, I get this sum equals 0, right? So we get, if I just rewrite this, we have sigma summation over the sample index, xi minus mu hat ml equals 0. So that's going to become summation over sample index of xi. So I'm going to move this negative mu hat ml in the summation to the right side. Right. But then this doesn't depend on I, so it's just going to be capital N times mu hat. Right. So this is just capital N times mu hat. And from that you get your, divide by N, you get your sample average. Right. So you're from here, going around, mu hat ml is 1 over N xi. Right. So regardless of the value of sigma, the covariance matrix for this model, the maximum likelihood estimator for the mu parameter is the sample average. And it also happens to be the mean value of the random vector. Okay, so So then you're probably wondering, is sample average always a good estimator for the mean of a random vector? Is it? Should we always do sample averages to estimate the mean of a PDF? Well, because I'm asking it, the answer is probably no, right? Yeah. So let's look at the covariance of mu hat to see why it might be no, right? Okay. So because these are random samples and we're passing them through this function, mu hat is random. So it has a PDF of its own. Well, actually, because in our case xi's are random, we add up. Sorry, Gaussian. We add a bunch of independent Gaussian random vectors, so mu hat is a Gaussian PDF, has a Gaussian PDF as well. Right, so let's see. Let's see what the parameters of that Gaussian PDF is. Right, so mu hat ml is Gaussian. It's a random quantity with some mean, expected value of mu hat, whatever it is. Right, and some covariance matrix. So I'm going to just write covariance mu hat. Okay, so let's figure out what those are. So expected value of mu hat equals expected value of, and these expectations are with respect to the joint, with respect to the entire data set, right? So if I make it more clear, it's going to be x1 to xn. So these expectations are with respect to the data set. So, which means if you really wanted to analytically express this, this is integral, right? 1 over n from 1 to n xi, right? That's my mu hat, which is a function of xi's. And then the expectation is with respect to the joint of x1, x2, x3, right? So the joint x1, xn, right? So all of those. Okay, so that's, so when I write expected mu hat conveniently here, I mean all of that, right? Okay, so let's plug in 1 over n summation over I xi. Okay. So expectation and scaling and adding are all linear operators, so I can switch the ordering in any way I like. So I'm going to take these to the beginning part here. So expected value of xi. Okay. So expected value of xi with respect to all those is mu, right? So the true value is mu. So this is equal to mu, and I have 1 over n. Capital N, 1 over n times mu, which is mu. Okay, so expected value of mu hat is mu. Okay. When we have a parameter estimator such that expected value of the parameter estimator is equal to the true value, so expected value of mu hat equals mu. So when this happens, we call that estimator unbiased, which was in the practice question, right? So this is an unbiased estimator. Right, so on average, you get the correct value. On average meaning if you repeated the experiment drawing data sets many times, get the estimators, and average those estimates, right? So you would, those would end up being the true value. Okay, so if the expected value of the estimator is not equal to the true value, then we call it biased, right? So if you have inequality, then that's biased. So people tend to like unbiased estimators. Right? You feel good about yourself knowing if you did this repeatedly, on average, things are going to end up being correct. Okay, so let's look at the covariance of mu hat. So covariance of mu hat is expected value. Again, that's expectation with respect to the entire data set, right? Of mu hat minus expected value of mu hat, which is mu, right? So mu hat minus mu. So that's the expected value of mu hat, and mu hat minus mu transpose, right? So that's the covariance. And so this will be expected value of, yeah, let's just trying to decide if it's easier downstream to keep it like this or split it. Anyway, let's keep it. So let's plug in mu hat. So this is expected value of 1 over n summation over samples xi. So that's mu hat and minus mu, right? So I can actually write this mu as 1 over n summation over I mu, and then just merge these, right? So it becomes xi minus mu in parentheses. So I'm going to do that. So yeah, so that's mu hat minus mu, and I'm going to just transpose it and write here xi minus mu transpose. So the whole thing transposed. Okay, so if let's use index j here. So if I do the multiplication of these sums, I'll get a double summation, 1 over n squared, summation over I, summation over j, these terms with xi multiplying these terms with xj transposed inside an expectation. And then I'm, again, scaling, and all those double sums with expectation can be swapped. So I'll just do all of those at once. So covariance of mu hat is equal to 1 over n squared summation over I over j expected value xi minus mu xj minus mu transpose. Yeah. So and that's covariance of x for every I and j. This is expectation over the whole data set. Anyway, so you can show that this is equal to that sigma matrix, right? So this is equal to sigma, the covariance. So this becomes 1 over n squared summation over I, summation over j, the covariance matrix of x. So this is n squared times sigma divided by n squared, so it's equal to the covariance of. Actually, I think we're missing an n. I think this should be 1 over n. So where's the mistake? So there must be a mistake somewhere, because so I'm missing a squared. It should be, might be introduced here, because from here to there it's just shuffling things, right? N squared. Oh, I think it might also be there actually. When I is equal to j. I actually solved this in the practice solutions that I sent out. I solved it by expanding, and then everything worked out fine. Okay, so there is a mistake either introduced here or that step. So I'll fix it and tell it should be 1 over n. So let's not waste time here. So here's the mistake. If somebody finds it, let us know, and I'll try to do it not in a rush at my office. Okay, so it should be 1 over n times covariance. Okay, so covariance of mu hat should have been 1 over n times the covariance of x. So if the covariance of a parameter estimator as n goes to infinity, as number of samples goes to infinity, if the covariance of the parameter estimator goes to 0, like in this case, assuming sigma is a finite, sigma has finite eigenvalues, so finite values in it, then we call this an asymptotically consistent estimator. Right, so this is asymptotically consistent, meaning as you perform your estimation with increasing number of samples, the variations from that mean value will diminish towards 0. So that's a good thing, right? So if you don't have an asymptotically consistent estimator, again, that makes us nervous because I'm throwing in more data into my estimator, yet even with infinitely many samples, I will have this randomness in the estimator, which is really undesirable, right? So unbiased, or if you cannot get unbiased, asymptotically unbiased, right? So are acceptable, and asymptotically consistent is also a desirable property. So if your asymptotically unbiased is the same as defined similar to this one, asymptotically unbiased would be your estimator, which depends on the number of samples, has an expected value which goes to the true value as n goes to infinity. Right. So as you throw in more samples into the estimator, the expected value becomes equal to the true value. But for finite number of samples, it might not be unbiased. Right. So it only becomes asymptotically unbiased as you throw in more and more samples. So why do people like the ML estimator? Because if your data actually comes from the assumed parametric PDF function, then the ML estimator is asymptotically, in general, unbiased and asymptotically consistent. So in this case, it turned out to be unbiased for every number of samples. That doesn't happen in general. So in general, it's asymptotically unbiased, meaning for finite number of samples, your ML estimate will be biased, probably, but that bias will go towards 0 as you use more samples. It actually has another nice property, which is not about which is about efficiency. Let me say. So to talk about efficiency, I need to mention something called Cramer-Rao bound. Sometimes it's called Cramer-Rao lower bound. Basically, if you have I think historically what happened is Rao invented the bound first in India, and then Cramer invented it independently in England. But then Cramer's invention was known earlier. Then people discovered, oh, Rao was also there actually before, so it was named after both of them, but in order of becoming popular. So so it's a really good bound actually. It tells you what's achievable. Right? So if you have a data set, let's say, let me just say X. If you have a data X that's thought to come from a PDF with parameter theta, and if you have an unbiased estimator, So let's say theta hat as a function of your data is an unbiased estimator. All right, so it's an unbiased estimator of the parameter theta. Then, so this is any unbiased estimator. There are more than one. There are infinitely many possible unbiased estimators. So then the covariance of this unbiased estimator, I'm going to stop writing x, is minus something called the Fisher information matrix inverse, is always positive semi-definite. Okay, so this is a positive semi-definite. Okay. People typically write this as covariance of theta hat, where theta hat is unbiased, is greater than or equal to Fisher information matrix inverse. I mean, it's an abuse of notation, right? Because you cannot have a matrix be greater than another matrix. You have to specify in what sense, right? So this is the sense that they're talking about here. So if you subtract the Fisher information matrix from the covariance of the estimator, of the unbiased estimator, then that matrix is positive semi-definite. So this has very nice implications, very useful implications. For this matrix to be positive semi-definite, first of all the diagonal entries must be non-negative. Right? So a diagonal value of this covariance matrix is the variance of the corresponding parameter. Right? So if you look at covariance theta hat diagonal entry I, it's the variance of the estimate for parameter I. Right? So what this implies is covariance of theta hat diagonal I minus Fisher information inverse diagonal I minus Fisher information matrix inverse diagonal I must be greater than or equal to 0. Which means, and by the way, Fisher information is a positive definite matrix, so its inverse is positive definite. So this is a positive quantity. So variance of the estimate for parameter I must be greater than or equal to Fisher information matrix inverse diagonal entry I. Okay, like that, which is greater than 0. Actually, it can be 0. Okay, so it puts a lower bound on the achievable variance for an estimator that's unbiased. There are extensions of this which are suitable for estimators that are not unbiased. So for biased estimators, you need to take into account the Jacobian of the estimator somehow in here. Actually, you can find it online easily. I don't remember the expression, so I don't want to write it up. But the implication of this is if you care about unbiased estimators, according to this theorem, you cannot achieve less than this much variance for your parameter. So what is this Fisher information matrix? How do I find that number? In general, it's not easy to compute. Okay, so the Fisher information matrix is the expected value with respect to the PDF of your the PDF that you're assuming for the data, the P of the Hessian. Of the Hessian. So I'm going to write this of the log likelihood. Okay, which with some mild assumptions about the PDF behaving well under inside integrals, because this is an integral, right? So they usually say in math, under mild assumptions. So in practice, people always assume that these mild assumptions hold, and then we use this, right? So this is expected value of gradient. So this is column. Let me make this transpose here. So it's a column vector. So it's a column-shaped gradient of the log likelihood. Then row, so transpose of that. Right, so it's the gradient in a column, gradient in a row multiplied, and then expected value. Right? So it tells you something about the curvature of the model in this theta coordinate frame system, right? And yeah, so if you can compute this matrix, if you can compute this expectation, then you invert it, and you have your lower bound. So maximum estimators that achieve equality. So the covariance is equal to the Fisher information inverse matrix. Those are called efficient estimators because this is the smallest possible variance you can achieve. So if you have an unbiased estimator that achieves the smallest possible variance, it's using the data very efficiently in this sense, right? So in general, achieving the Cramer-Rao bound for every finite number of n is not easy, is not possible. So we typically can settle for asymptotic efficiency, right? So as number of samples, again, this depends on number of samples. So as number of samples go to infinity, if this difference goes towards 0, then that estimator is called asymptotically efficient, right? So which is pretty good. So ML estimator, theta hat ML for a parametric model like this is, so we talked about asymptotically. So in general, asymptotically, okay, unbiased, efficient, and consistent. I'm actually, I'm pretty sure about this one, but I'm going to go check the textbook to make sure. So it has really nice asymptotic properties, right? As you throw in more data into the ML estimator, it gets better and better, right? So the expected error goes down to 0, expected variance, variance goes down to 0, eventually to 0 probably. So it has really nice properties asymptotically, therefore people like it, and it's used a lot. Okay. There is one more nice property of maximum likelihood estimation. Okay. So just before I go there, just one side note. If you see papers, so there's a field called active learning. Which specifically deals with trying to design algorithms that ask smart questions to improve the speed of learning that they go through, right? So if I have a machine learning algorithm that's trying to solve a problem, in active learning, I will give the algorithm a chance to ask what label it needs, as opposed to me giving it, here is some data for you, right? So Fisher information matrix is used in some objectives that are used in active learning strategies as well. They're called querying strategies. The algorithm says, give me a label here, give me a label for this data sample. And because of this relationship to parameter estimation accuracy, it's a very nice matrix to exploit for active learning techniques. And you'll see some Fisher information matrix-based active learning strategies, right? As a side note. Okay, so back to another nice property of ML estimation. Remember, we talked about reparameterize. We talked about reparameterizing the Gaussian PDF. Instead of using the covariance matrix, use the precision matrix to express the PDF, right? So I can have this parameterization. So P of X is that. That's your mean covariance matrix parameterization of the Gaussian. Or I could reparameterize this PDF and use the precision matrix, which is inverse of. Oops, sorry, that's gamma. Inverse of the covariance matrix. So you can use the precision matrix instead of covariance, and so this would become gamma positive square root, and this sigma inverse would just become gamma. So this is an This is called an invertible. Right, and this is implicit. Right? So this is an invertible mapping between two sets of parameters. Right? If I give you the gamma matrix, you can figure out the sigma matrix, or vice versa. And typically, when optimizing parameters for Gaussian PDFs, using the precision matrix parameterization leads to better behaving numerical optimization outcomes, because you don't need to deal with taking derivatives through this matrix inverse. Right? So simpler expressions and probably better convergence too. So you can take a PDF which is parameterized by theta and reparameterize it. Okay, so I'm gonna take this PDF which has parameter vector theta. I'll define a new set of parameters with an invertible function. So I'm gonna say f inverse exists and gamma equals f of theta. So I want an invertible function which takes vector theta and produces vector gamma. And I use now gamma to describe the PDF. It's the same PDF, right? It's exactly the same PDF. I'm just using a different set of parameters. Just like here. So when you have this kind of reparameterization, there is a nice property about maximum likelihood estimation. Maximum likelihood estimate of gamma is equal to f of maximum likelihood estimate of theta. Okay. So maximum likelihood estimation basically is invariant to invertible reparameterizations, right? So you can reparameterize the problem, solve the maximum likelihood estimate for a different set of parameters, because maybe your optimization problem is easier for gamma, right? Once you find gamma hat ML, you pass it through F inverse, you get theta hat ML. Right? So you can go back and forth between parameterization depending on whichever parameterization suits you for the particular step. The proof is relatively easy, and I can write it up separately and send around. But basically, it depends on so if you think of maximum likelihood as an optimization problem like we have been doing, right? So basically what we're talking about here is solving these two problems. And saying that they satisfy this relationship. So you can, for example, if I assume these are differentiable twice with respect to theta and gamma, I would go to the gradient and Hessian and show that a solution that satisfies the optimality conditions to first and second degree for gamma passed through the inverse of f would satisfy the first and second order optimality conditions for the first problem. So show that a solution of this problem passed through the function is a solution of the other problem. I mean, it's a little cumbersome, but it's not conceptually hard. Okay, so that's another nice property of maximum likelihood estimation. In addition to these asymptotic properties, that makes this attractive. Okay. So map estimation, for example, does not have this property. So let's look at map estimation for this Gaussian PDF. Okay, so our data set, again, condition on mu. So given mu, I have this Gaussian PDF assumption for my data. And now I would like to assume something a priori about the value of mu. So I'm going to assume that mu itself is a random vector that has a Gaussian prior. So, and I'm going to call that Gaussian normal MC, right? So the expected value of mu is m, and covariance of mu is c, before we observe any data. So my map estimator, mu hat map, will maximize the log likelihood plus log prior, right? And we wrote the log likelihood before, so let's just quickly write it again. So this is going to be summation log something with 2 pi, something with sigma minus 1 over 2 xi minus mu sigma inverse minus mu. Okay, so our log likelihood look like this, right? So log, so yeah, log something with 2 pi, something with sigma minus this. Okay, so now let's add the log prior plus, and this prior is 2 pi negative n over 2 c e to the power mu minus m c inverse mu minus m, right? So mu itself is a Gaussian random vector, so it has its own prior PDF. So log prior is, again, log of that, so something with 2 pi plus something with c and minus 1 over 2 mu minus m c inverse mu minus m, right? Okay. So remember, we drop these additive constants that don't depend on mu because they just change the value of the function, not the location of the optimum. And we then multiplied with negative 2, so I can do the same thing here. So to get rid of this division negative sign, that becomes a minimization problem. Right? So equivalently, my map estimator will be the following. So mu hat map is going to minimize summation xi inverse I minus mu. Okay, so that's the likelihood part, and this is the prior part. C inverse mu minus mu. Okay, so mainly we added log p of mu to the objective, because now we have a non-uniform prior, and that ended up giving us this additive term, which came from the prior, right? So it's the same as maximum likelihood plus some kind of extra term. Typically, in machine learning, people call these additive terms that try to keep the estimates of a parameter under control. In this case, it's kept under control by forcing it to be close to m, right? So the Gaussian prior here says mu should be in the vicinity of m, and how far you can get away is controlled by c. Right? So if c has large eigenvalues, large eigenvalues, so along the directions of those large eigenvalues, eigenvectors, you can get away from m. But if c has small eigenvalues for some eigenvectors, in those directions you cannot get away from m, right? Because it's going to get really unlikely. So, so this prevents deviating from m too much, according to this expression, and this is called a regularization term. Yeah. So the priors in map estimation, log prior is like adding a regularization term to the ML objective. So to keep things from deviating too much from what you think is probably a correct value. Right? Okay, so let's take the derivative again, because still we have a quadratic function of mu plus quadratic function of mu. So I'll take the derivative, equate to 0. Okay, so of the derivative of the summation, first summation, plus derivative of the second. Okay, so we did this first part before, so I'm just going to write it. So equals, okay, so this will be negative 2 covariance sigma inverse summation over sample index I, xi minus mu, and that one will be, so mu now has a positive identity multiplying, so it's going to be plus 2c inverse mu minus m. And this will be equal to 0 at the map estimate. So I'm going to just substitute here mu hat map, mu hat map. Okay, so that's my map estimator. It's going to make this gradient 0. So since 0 is equal to 2 times something, I can drop the 2's. Actually, negative 2, right? So 0 equals, so I can actually, so now we have a sigma inverse. Okay, so now we have sigma inverse. Let me also divide by n. Divide by, so 1 over n. So I divide by n, it's still 0. So here we have sigma inverse 1 over n summation xi, and n times mu hat divided by n, so it's going to be just minus, hopefully I'm doing this right, so make sure you're checking on the way, mu hat map, right? So the division by n and the summation over I multiplying mu hat will become n times mu hat, so they cancel. And here we have plus, yeah, I think I'll just keep it like C inverse n mu hat map minus m. I'll keep it like that for now. So we notice here, this is the maximum likelihood estimate. So we have a relationship between the map estimate and the maximum likelihood estimate, right? So I'm just going to plug in here, in this case, that's the maximum likelihood estimate of the mean, just so that we can relate the two. So our maximum likelihood estimate was 1 over n. That was a sample average. So here we have, so if I move these mu hat map terms to the other side, we have I'm hoping there is no negative mistake here, like a sign mistake. Okay, so we have sigma inverse, so sigma inverse mu hat map minus C inverse over n mu hat map, right? So move those to the left, is equal to sigma inverse maximum life sample average minus C inverse minus 1 over n C inverse n, right? I think that's correct. And so if this matrix is invertible, then I'll just multiply with the inverse of this. So that's inverse of that matrix times sigma inverse sample average minus. Okay, so you get some expression. But basically, I mean, if you expand it, you see this is equal to, if you multiply, you can use here matrix inversion lemma. Does everyone know what matrix inversion lemma is? I'll just show it to you. Sometimes it's called Woodbury identity. Let's quickly check it out. So matrix inversion lemma will give me from here something like sigma plus stuff, okay, and then sigma inverse we had ml minus 1 over n C inverse m. Okay, let's just check it out to quickly see. I didn't log in for a long time. Okay, so while waiting, so this will be sigma plus whatever. So when I multiply these out, this sigma inverse maximum likelihood estimate. So I'll just, the sigma and sigma inverse will cancel, so I'll have maximum likelihood estimate plus a bunch of other stuff. Right, so there will be a, let's say, an augmentation of the maximum likelihood estimate due to the prior that's pulling my estimator towards m, right? Because what the prior says is your estimate should be close to m, and what the data says is your estimate should be close to the maximum likelihood estimator, and now map is trying to find a balance between what the data says and what the prior says. Right?
So where do I get my prior estimations m and c?
You make it up. You make it up in an appropriate fashion. So, well, I mean, you should not make up bad priors. So that's the lesson to be learned from this, actually. So let's first see the matrix inversion lemma, and I'll talk about it. This is okay, let's check this one. Yeah, so I'm hoping you can see this. Okay, so when you have an invertible matrix A plus 3 matrices multiplied, U, C, B, and C should also be invertible. Right? So, and you're trying to invert that kind of summation of matrices multiplied and added. Okay, so you can expand it into this this expression on the right. Right? So here that A is our sigma inverse. U, C, V, that's this. So that C could be C inverse over N. U and V, in my case, are identity. Maybe negative identity, or I can say C is equal to negative C inverse N. U, V both equal to identity. Right? A is equal to sigma inverse. So now I have exactly that situation. So I'll have sigma minus sigma identity for U. That C is my negative C inverse N. So inverse of that will be NC, negative NC. Right? So you just do that. And anyway, I care about this part. Right? So sigma plus something. So I'll have sigma plus whatever. That takes a thing. And when I multiply out, I'll get my maximum likelihood estimate plus 3 other terms. Okay. So you can do it for fun later. But the lesson to be learned is exactly what you're asking. So if you, depending on what you choose for your prior, this map estimator can be very close to the maximum likelihood estimator or can be forced away from it. Right? If the prior says, if M is away from the maximum likelihood estimator, then the prior, and if you choose C to be small, to have small eigenvalues, the prior is very confident that mu should be very close to M. Whatever the data says, because the prior has equal weight in the objective, right? So we had log likelihood of the entire data plus log prior. And these are equally important for you. So the prior will pull you away from the maximum likelihood and towards the mean. So to overcome the prior, you would need to increase the number of samples towards infinity. So let's look at what happens here as number of samples go to infinity. Okay, so this I'm going to take the limit as number of samples go to infinity of my map estimator, which depends on, which is a sequence indexed by n, right? So this first term, so C inverse is a finite matrix, so n goes to infinity. This goes to 0. So I have sigma inverse is sigma, right? So this matrix goes towards sigma. And here I have sigma inverse maximum likelihood estimator. And this additive term here also goes to 0 because this C inverse M is a finite vector, finite length vector, and divide by n, which goes to infinity, right? So this is equal to ml. So in general, when you throw in more data to your map estimator, more independent data, right? Eventually, those data samples will overcome the prior, and you'll end up with the maximum likelihood estimator. So theta hat map will go to theta hat maximum likelihood as n goes to infinity. So because the effect of the prior will go down towards 0. To see this in the objective, let's write it out. Well, actually, I don't need to write it. I have it here. Let's pull this back up. Okay, so if I have multiple samples that are independent here, right? So let's look at this. So my theta hat map, when I have n samples, n independent samples, will be maximizing log. I have independent samples, so I'll be multiplying these, and then I'll have the prior giving me a preferred value, right, based on the prior PDF that I choose here. So this will be summation so if I divide this by n, okay. So here, what I have here is a sample average of log likelihood, right? So as n goes to infinity, this goes to, if this sample average converges, then this goes to expected log likelihood of x, right? So this goes to expected value of log p of x, right? Which is exactly what this does, right? So that's the maximum likelihood objective as n goes to infinity. So you can do the same thing here, and so this goes to expected log likelihood. And this term here, that term goes to 0, right? Because this n goes to infinity, and this log p is finite, right? Fine. So it goes towards 0. So eventually, even if you choose a wrong prior, like wrong meaning bad in some sense, right? Then if you have enough data, you'll be able to overcome that incorrect choice of the prior. But in practice, of course, you don't want to do that, right? The whole point of this prior is to help you estimate parameters accurately with small number of samples. It's not to put in a function there and then hope that it's good, and if it's bad, you need more data. So how do you choose the prior? Typically, this should be informed by your operating conditions about whatever situation you're dealing with. In the past, one common practice has been to choose what's called a conjugate prior. So we'll talk about it more later, tomorrow. Because it actually makes this posterior analytically tractable. I'll just write it out and then stop. And we'll pick up from here tomorrow. So remember, we're all about getting the parameter posterior, which is likelihood of theta given data set X. And remember, this is equal to P of from Bayes rule. This is equal to that. And remember, this normalization denominator here is an integral of the numerator, right? So integral so this is an integration. This is a definite integral over all the values of theta. So maybe negative infinity. So so a conjugate prior make this integral analytically tractable, right? So for example, in the example we did, theta was the mean vector of a Gaussian, and I chose a Gaussian prior for mean, right? So a Gaussian prior for the mean of another Gaussian forms a conjugate prior situation. So this integral becomes analytically possible to solve. So people chose these conjugate priors for, so you choose this, and then you choose a conjugate prior for your appropriate, that's appropriate for your parameters. Then, of course, the conjugate prior itself has these other parameters, MC in that case, which you have to somehow choose based on how much you want to trust the prior versus how much you want to trust the data. And that's typically, that's done by some hand-waving approaches. Sometimes those are called hyperparameters. You can use cross-validation procedures to set those parameters. You can think of those parameters of the prior as yet more parameters to estimate. So you can use maximum likelihood estimation to estimate those parameters. Yeah. So instead of picking them, you can say let the data decide. So for those things, you need to create these cross-validation experimental scenarios, which we will talk about later. So at that point, we can mention this again. So if you choose conjugate priors, this this has a closed form expression. So you can actually plug that in here, and so this has a closed form expression, this has a closed form expression, and this also has one. So now you have a closed form expression for the posterior. So that was very desirable in the 90s. So everybody used conjugate priors. And then some people were saying, well, but why do I use a conjugate prior? That's just out of convenience. So to make this tractable, I really want to use this other prior because it suits my problem better. For those techniques, you need to then numerically approximate these integrals. So that leads to these Monte Carlo, Markov chain Monte Carlo methods, which again in the 90s and 2000s were really heavily studied. So yeah, so choosing the prior is not easy. Let's stop there. So choose it well, wisely.